Every building, bridge, or dam you pass by hangs on a thread of engineering math. Formulas and blueprints form the invisible skeleton of our civilization, a framework we trust blindly every single day. We step into elevators without thinking about the cables, and we sleep beneath massive dams without wondering how many millions of tons of water are pressing against the concrete just miles away. But when a glitch occurs, the consequences change history. And usually, nature isn't to blame. The blame belongs to specific people who knew about the flaw and chose to stay silent. Our first story was hidden by the Chinese government for nearly 3 decades. In August 1975, the Banqiao Dam stood over 30 meters high in Hunan province, holding back 500 million cubic meters of water. Built in the 1950s with Soviet assistance, it was designed to survive a once-in-a-thousand-years flood. However, during construction, a hydrologist named Chen Xing warned that the drainage gates were too small. He was labeled a pessimist and kicked off the project for delaying the schedule. 20 years later, Typhoon Nina hit. It stalled directly over Hunan, dumping a full year's worth of rain in just 24 hours. The deluge was a once-in-2000 years event, twice what the dam could handle. Water rose so fast that silted, neglected sluice gates failed to open. On August 8 at 1:00 a.m., the Banqiao Dam collapsed. A wall of water 10 kilometers wide and 10 meters high rushed down the plains at 50 kilometers per hour. Communication lines had been destroyed by the storm, so sleeping villagers received zero warning. The wave wiped out entire towns in seconds. Following Banqiao, 62 other dams failed down the line like dominoes. Over 10 million people were stranded without food or clean water. While official reports unsealed in 2005 claimed 26,000 drowned at night, independent estimates placed the total death toll at 240,000 due to subsequent famine and epidemics. On January 28, 1986, an unusual freeze hit Cape Canaveral, Florida. Temperatures dropped below zero as the Space Shuttle Challenger prepared for launch. On board were 7 astronauts, including Krista McAuliffe, a schoolteacher set to become the first civilian in space. Millions of schoolchildren across America were watching live. The night before, an engineer named Roger Boisjoli from Morton Thiokol, the company that built the solid rocket boosters, held an emergency meeting with NASA. He begged them to scrub the launch. The rubber O-rings sealing the booster joints lose their elasticity in freezing temperatures. If they fail, hot gases will burn right through the rocket. Boisjoli presented hard data and past test results. But postponing the launch again was deemed too expensive and politically embarrassing. Under intense pressure, Morton Thiokol management blinked. They famously told their team to take off your engineering hat and put on your management hat. The timeline of failure. Midnight, Challenger launches in freezing conditions. 0:58, plume of flame escapes a compromised O-ring joint. 00:73, hot gases ignite the main fuel tank, the shuttle disintegrates at 15 kilometers altitude. The crew capsule plummeted into the ocean, killing everyone on board. During the public investigation, Nobel physicist Richard Feynman exposed the truth simply by dropping a piece of the O-ring rubber into a glass of ice water on live television. It hardened instantly, losing its seal. Roger Boisjoli spent the rest of his life lecturing on ethics. He told students, when an engineer says no, that must be the final word. Physics does not negotiate with budgets. It was Friday night, July 17, 1981, in Kansas City, Missouri. The 40-story Hyatt Regency Hotel was a marvel of modern design, famous for its massive, sunlit atrium. Suspended from the ceiling by steel rods were 2 pedestrian walkways, the sky bridges, located on the 2nd and 4th floors. Around 1,600 people gathered in the lobby for a dance contest. Dozens of spectators crowded onto the sky bridges to watch the dancers below. Suddenly, a sharp metallic crack echoed through the room. The 4th floor walkway tore away from its rods, crashed down onto the 2nd floor walkway, and both collapsed into the crowded lobby. It took rescuers all night to pull survivors from beneath tons of steel, concrete, and glass. The cause was tragically simple. The original blueprints called for a single continuous steel rod to run from the ceiling down through both walkways. During construction, the contractor altered the design to two separate rods to make installation easier. This minor paperwork change doubled the load on the fourth-floor connection. The structural engineers approved the change over the phone without recalculating the stress. Nobody checked the math. On May 16, 1968, the 22-story Ronan Point apartment tower in East London had been open for just 2 months. It was the flagship of Britain's post-war prefabricated housing boom. The government paid developers extra subsidies for every floor built above the 20th, sacrificing quality for speed. At 5:45 a.m., Ivy Hodge, a cake decorator living on the 18th floor, went to her kitchen to make tea. She struck a match to light her gas stove. A spark ignited a minor gas leak caused by a faulty brass nut. The explosion itself was relatively weak. Ivy survived with minor injuries. But when she opened her eyes, her kitchen walls were gone. She was staring into the open air from 18 stories up. The blast had popped out the load-bearing concrete panels of her apartment. Without support, the 4 floors above her collapsed one by one, pancaking straight down to the foundation. 4 people died in their beds. The inquiry revealed that the tower was essentially a house of cards. The massive concrete panels were stacked with almost no structural links holding them together. Shockingly, builders admitted they stuffed empty tin cans and rolled up newspapers into the joints instead of structural mortar. This disaster forced a complete rewrite of global building codes, inventing the concept of preventing progressive collapse. On July 1, 1940, the Tacoma Narrow Suspension Bridge opened in Washington state. Spanning 1.5 kilometers, it was praised as an elegant, slender masterpiece of modern engineering. But right from the start, drivers noticed something unsettling. Even in light breezes, the road deck would ripple and bounce like an ocean wave. The bridge earned the nickname, Galloping Gertrude. Engineers observed the movement but assumed it was harmless, planning to add dampening cables later. They ran out of time. On November 7, 1940, a steady 65 km/h wind hit the valley. The wind speed matched the natural vibration frequency of the bridge, causing a phenomenon known as aeroelastic flutter. The motion changed from a simple up-and-down bounce to a violent, twisting tear. One side of the road deck would rocket up while the other plunged down. The concrete and steel twisted up to 45 degrees. The last man on the bridge, journalist Leonard Coatsworth, had to crawl on hands and knees to escape, abandoning his car. The steel support cables snapped like guitar strings, and the entire center span tore loose, plunging into the Puget Sound below. The event proved forever that aerodynamic forces are just as lethal to structures as gravity. On April 26, 1986, operators at the Chernobyl nuclear power plant in Ukraine initiated a routine test on reactor number 4. They wanted to see if the spinning residual inertia of the turbines could generate enough electricity to power the cooling pumps during an emergency blackout. To set up the test, operators deactivated several automated emergency safety systems and dropped the reactor's power to an unstable, low level. What the operators did not know was that the Soviet RBMK reactor had a critical design flaw. Its creators knew about it, but the defect was classified as a state secret to protect the USSR's reputation. When the shift supervisor finally pressed the emergency shutdown button, AZ5, to drop the control rods, the graphite tips caused a localized power spike instead of stopping the reaction. Within 4 seconds, the power surged to catastrophic levels. A massive steam explosion blew the 1,000-ton concrete shield roof straight through the ceiling. A second explosion threw burning radioactive graphite and nuclear fuel high into the night sky. Firefighters arrived without radiation gear or dosimeters, extinguishing fires with water while standing on glowing pieces of nuclear core. Most died agonizing deaths within weeks. The resulting radioactive cloud contaminated vast areas of Europe, leaving a 30-kilometer exclusion zone that remains uninhabitable today. On August 14, 2018, a torrential rainstorm hit the port city of Genoa, Italy. Driving visibility dropped to near zero on the Morandi Bridge, a critical highway link connecting Italy to France that carried over 25 million vehicles a year. At 11:36 a.m., without warning, one of the main cable-stayed towers snapped. A 200-meter section of the highway, along with dozens of cars and heavy trucks, dropped 45 meters onto the railway tracks and buildings below. 43 people died on their morning commute. The investigation discovered that the steel tension cables inside the concrete stays had been slowly corroded by salty sea air and industrial smog for 50 years. The bridge's designer, Riccardo Morandi, had written an official warning before his death in 1989 stating that the structure required constant maintenance due to concrete degradation. During the trial, the former head of the maintenance operator admitted under oath that an internal report explicitly warned of a collapse risk 8 years prior. He chose to hide the report to protect company profits and his personal executive position. Every single engineering disaster we examine shares this exact same pattern. Someone knew. The technology itself rarely fails on its own. It fails because humans cut corners, ignore warnings, chase deadlines, or prioritize corporate budgets over human lives. The thin line protecting us from catastrophe isn't concrete or steel. It is the ethical integrity of an engineer willing to stand up, risk their career, and say, no.